Greetings, my name's Long. I'm going to present Bike Aero 101, Fundamentals of Speed. Aerodynamic drag. So aerodynamic force is the force that opposes the forward motion for a bike and rider. And it's defined as follows. Drag equals 1/2 rho, pressure density of air, times velocity square times coefficient of drag times the area incident to airflow. Pressure density, so that's the unit of air at standard room temperature. So one slug, this is not the slug in your household that eats your vegetable garden. This is the slug that is used for determining what 1 pound of force is accelerated at 1 feet per second square. And this is used in the British units. So at 0 feet elevation, we have 23.77 times 10 to the minus 4 slugs per cubic feet for air density. If you notice at 5,000 feet, it's a little bit less. So bicyclists in Denver has a little bit less air density to create drag against. On the other hand, they also have less oxygen to breathe also. If you notice also on the table here at 35,000 feet, the density is only 7.38 times 10 to the minus 4 slugs per cubic feet. That's where airlines cruise at because the density of air is so low. Velocity, this is the forward velocity for which a bicyclist travels at. The units is in miles per hour because we're in the US, where the rest of the world uses kilometers per hour. Coefficient of drag. So this defines how efficient an object moves through air. Some examples are sphere, half sphere, long cylinder, short cylinder, streamlined body, and half streamlined body, and their drag coefficient. So a human bicyclist will have a drag coefficient more similar to a sphere than a Boeing 787. If you cut a cross section of human, it's more round. So by comparison, Tesla Model 3 has a CD of 0.23. That is excellent for a car. And a Boeing 787 has a CD of 0.024. That's 10 times better than a Tesla Model 3. So coefficient of drag here. Position of bicyclist, whether he or she is tucked or in an upright position, has great effects on the coefficient of drag. And since drag varies as a speed squared, the faster a bicyclist rides, the more impact drag has on speed. What you want to do is to position yourself to make it a more streamlined body to the air. Typical rider has an effective frontal area of about 4.4 to 7.6 square feet. So the posture of bicyclists will impact the effective frontal area. The clothing and accessory that bicyclists wear also affect the effective frontal area. Let's talk about a typical rider. We're assuming 50-pound bicyclist riding at 15 miles per hour. That's 22 feet per second at sea level. He or she has a CD of 0.65. That's a little bit higher than a sphere. An effective frontal area of 5.4 square feet. So if you calculated this out, so pressure at sea level, standard room temperature, 22 feet per second square times 0.65 coefficient of drag times 5.4 square foot area, that turns out to be 65 pound-feet of force. Compare this to, let's say, an engine of a 787. So one engine has 75,000 feet-pound of force at sea level. So this is fairly small, 65 pound-feet of force. So how much power is this force equivalent to? So 1 feet-pound of force per second is equal to 1.3558 watts. So to compute this power for 1 second, we have 88.1 watts. So right now we're assuming friction due to mechanical and tires are linear and small for a road bike. A fat bike may be significantly different. And then most of the power to overcome drag at higher speed and the mechanical and tire are fairly small at higher speed compared to drag. So I plotted this typical rider with an effective frontal area of 5.4 square feet and a drag coefficient of 0.65. If you notice at 10 miles per hour, the drag wattage is about 40 watts. And at 20, it's about 160. So that's quadruple the power needed if you're just doubling the speed from 10 miles per hour to 20 miles per hour. That is significant. It goes much higher if you want to go 30 miles per hour. Pedaling power. So how much pedaling power is this typical rider going at 15 miles per hour? So let's assume a 171.5 millimeter crank. That's typical of a medium-size bicycle. And let's assume a cadence of 60 revolutions per minute. If you compute the pedal speed, that is about 1.08 0.38 meters per second. And the force of this pedal is just the power divided by the speed, and that turns out to be 58.8 newtons. 1 newton on Earth surface, sea level, is about 9.81 kilograms. And so the pedaling force required is about 6 kilograms or 13.2 pounds. This is a constant force you need to apply on the pedals at 16 RPM to generate the power necessary to overcome drag at 15 miles per hour. So what do we get out of this? So if you want to go faster, you can either work on increasing power through workout to increase your power, or reduce your drag. Faster you ride, the effects of aerodynamic drags has on the bicyclist increases. Before you go out and purchase the latest aero gear, whether it's a aero bike, aero helmet, aero clothing, aero shoes, perhaps you can work on posture and strength to increase speed. That will have a better return on investment. And finally, stay safe at whatever your speed. Thanks for watching.